Good day, everyone, and welcome to our presentation. I'm excited to introduce our research, Boosting Single Positive Multi-Label Classification with Generalized Robust Loss, a collaborative effort by Yanqi Chen, Chunxiao Li, Shenyang Dai, Jinwan Li, Weiyu Sun, Yiming Wang, Renyuan Zhang, Tinj Zhang, and Bo Wang. We've delved into the challenges of single-label multi-label tasks and have proposed a novel method, the GR loss, to significantly improve performance. Stay tuned as we unravel our findings and insights. In this slide, we delve into the key motivations and problems addressed in our research. Our primary aim is to enhance the performance of single-positive, multi-label learning, or SPML. This is a challenging task due to the presence of only one positive label, with the rest being unknown. This makes it difficult to predict unseen labels and handle imbalances. We also address the limitations of existing methods, such as AN loss and focal loss. These methods have shown to be ineffective in handling the imbalances inherent in SPML. Our research proposes a novel approach to overcome these challenges and improve the performance of SPML. Stay tuned as we delve deeper into our methodology and findings in the upcoming slides. In this slide, we delve into some key insights from our research. Firstly, we found that treating single-positive multi-label learning, or SPML, as multiple binary classification tasks can significantly enhance performance. This approach allows us to handle each label independently, which is particularly effective in datasets with fewer classes. However, it's important to note that this method may not perform as well on datasets with a larger number of classes and stronger label correlation. The more categories there are, the more positive labels each image has, which strengthens the correlation between labels. This can lead to a slight decrease in performance. These insights are crucial as they guide us in selecting the most effective strategies for different types of datasets in SPML. In the next slide, we will discuss how we address these challenges in our proposed framework. In this slide, we're going to delve into the key highlights of our research. Our main proposition is a new method known as the Generalized Robust Loss, or GR loss. This innovative approach involves determining hyperparameters and treating single-positive multi-label learning, or SPML, as multiple binary classification tasks. But what makes our method truly stand out is its use of a soft pseudo-labeling mechanism. This mechanism is designed to tackle two significant issues in SPML: false negatives and imbalance. By addressing these challenges, our method paves the way for more accurate and efficient multi-label learning. In essence, our GR loss method is a comprehensive solution that not only enhances the performance of SPML, but also provides a new perspective on tackling complex learning problems. Stay tuned as we delve deeper into the workings and results of this method in the following slides. In this slide, we delve into the key highlights of our research. Our primary contribution is the introduction of the Generalized Robust Loss, or GR loss, specifically designed for single-positive multi-label learning, or SPML. This novel loss function is a game-changer as it effectively addresses both intra-class and inter-class imbalance issues. To put it simply, it ensures that the model does not favor certain classes over others, and maintains a balance within each class as well. This is achieved through a unique approach of instance and class-sensitive reweighting. This means that the model adjusts the importance of each instance and class based on their distribution, leading to a more balanced and accurate model. Stay tuned as we delve deeper into how this works in the following slides. Begin our frame title key highlights, begin itemize. Item, our GR loss framework has been empirically tested and compared with state-of-the-art methods, showing promising results. Item, we conducted an ablation study of our framework and robust loss, and performed hyperparameter analysis. Item, an experiment was conducted to verify our assumptions using VOC and COCO validation sets. We divided 0-1 into 100 intervals and calculated the ratio of false negatives to missing labels. Item, the results showed that at the beginning of training, the scatter plot resembled a constant function, aligning with our first assumption. At the end of training, the scatter plot appeared as a monotonically increasing function, closely aligning with our second assumption. End itemize, end frame. In this slide, we delve deeper into the challenges of multi-label learning, or MLL. MLL is a powerful tool that constructs predictive models to assign multiple labels to unseen images. However, it's not without its difficulties. One of the main challenges is the acquisition of comprehensive labels for training. In many real-world scenarios, This process can be expensive and impractical. This graphic here, titled Gradient Analysis, visually represents some of the complexities we face in this field. As we move forward, we'll explore how we can navigate these challenges to improve the effectiveness of MLL. Let's delve deeper into Single Positive Multi-Label Learning, or SPML. This is a unique variant of multi-label learning where only one label is confirmed as positive for a given image. Now you might wonder, why is this important? Well, this scenario is not only more relevant to real-world applications, but it also presents a significantly greater challenge. As you can see in the figure, we've conducted a gradient analysis to better understand these challenges. In the following slides, we'll explore how we can effectively address these challenges and improve the performance of SPML. Begin frame. Frame title our solution. Generalized robust loss, GR loss, begin a figure, centering include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data. 2405.03501v1, figures 2405.03501v1 figure 2:1.png, captiona tinea GR loss performance on SPML benchmarks. End of figure. Begin itemize. Item introduction of our novel GR loss for SPML. Begin itemize. Item outperforms existing methods on VOC, COCO, and NUS benchmarks. Item achieves second highest result on CUB, slightly lower than MIME due to label correlation and interclass differences. Item designed to reduce the negative impact of noise and pseudo-labels. Item effectively mitigates both intra-class and interclass imbalance issues. End itemize. End frame. Begin frame. Frame title our solution. Generalized robust loss, GR loss, begin a figure, centering include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data. 2405.03501v1, figures 2405.03501v1 figure 2:1.png, captiona tinea GR loss performance on SPML benchmarks. End of figure. Begin itemize. Item our GR loss addresses the challenges in SPML. Begin itemize. Item it uses a soft pseudo-labeling mechanism to compensate for the lack of labels. Item it introduces two tunable functions to calibrate model output, dealing with both intraclass and interclass imbalance. Item it outperforms existing methods on most SPML benchmarks, but struggles with datasets with a high number of classes due to not considering class correlation. End itemize. End frame. Begin frame. Frame title a theoretical and experimental validation of GR loss. Begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data, 2405.03501v1, figures 2405.03501v1 figure 2:1.png, captiona tinea empirical results of GR loss. End of figure. Begin itemize. Item we validated the effectiveness of GR loss, both theoretically and experimentally. Theoretical validation includes deriving empirical risk estimates and performing a gradient analysis. Item experimentally, GR loss has shown impressive results, outperforming other methods on 4 benchmarks. Item however, there are areas for improvement. We need to explore dynamic robust loss, test GR loss on different backbones, and consider class correlation for better performance. End itemize. End frame. Begin frame. Frame title a theoretical and experimental validation of GR loss. Begin itemize. Item theoretical validation of GR loss includes deriving empirical risk estimates for SPML and performing a gradient analysis. Item experimental validation shows GR loss achieving state-of-the-art results on all 4 benchmarks. Item however, there are limitations to our study. Begin itemize. Item the robust loss parameters are static, but dynamic variation could improve balance between fitting ability and robustness. Item, we have not evaluated GR loss on different backbones, limiting the validation of its effectiveness. Item, our method does not consider class correlation, which has led to inferior performance compared to MIME on CUB. End itemize. Item, overcoming these limitations could significantly improve our work. end itemize, end iframe, begin iframe, frame title limitations and future directions, begin itemize, item our study, while promising, has three main limitations. First, the robust loss parameters Q1, Q2, Q3 are static. Ideally, these should be dynamic to balance fitting ability and robustness. Item second, we have not evaluated GR loss across different backbones, limiting the full validation of its effectiveness. Item third, our method does not consider class correlation, which has led to lower performance compared to MIME on Cub. Item addressing these limitations will provide significant improvements to our current work and is a key focus for our future research. End itemize, end iframe, In the realm of multi-label learning, or MLL, we face a significant challenge. Obtaining comprehensive labels for each training instance, this process can be both costly and impractical. As a result, we often have to work with incomplete labels, which leads us to a variant of MLL known as single positive multi-label learning, or SPML. In SPML, only one label is verified as positive for a given image, leaving all other labels unknown. This presents a unique challenge, as we must effectively deal with these missing labels. Despite these challenges, SPML is a highly relevant and practical approach to MLL, and it's the focus of our work today. Begin iframe, frame title our related works, begin itemize, item the challenge of incomplete labels in SPML, begin itemize, item SPML's incomplete labels present a unique challenge, often leading to oversimplified predictions where all labels are falsely identified as positive. Item pseudo labeling has been employed to address the issue of false negatives caused by the all negative assumption. End itemize, item dealing with label noise, begin itemize, item pseudo labeling can introduce label noise. To cope with this, robust losses such as generalized cross-entropy, symmetric cross-entropy, and Taylor cross-entropy have been developed. Item our method tailors robust loss specifically to SPML, aiming to effectively handle both false positive and false negative labels. End itemize, end iframe, In our exploration of related works, we find two primary strategies that have been employed to tackle the single positive multi-label learning, or SPML, problem. The first approach views missing labels as unknown variables that need to be predicted. This is indeed a challenging task, given that we only have one positive label to base our predictions on. The second strategy takes a different route. It assumes that the missing labels are all negative, effectively transforming the SPML problem into a fully supervised multi-label learning, or MLL, problem. This approach, while popular, can lead to oversimplification and the creation of false negative labels. As we delve deeper into our research, we'll see how we can build upon these existing strategies and propose a novel approach to address the unique challenges of SPML. In our exploration of related works, we've identified some key limitations in existing approaches to single positive multi-label learning, or SPML. Firstly, the all-negative, or AN, assumption is a common strategy, but it's a bit oversimplified. This assumption leads to a large number of false negative labels, which can skew the results of our models. Secondly, these false negatives aren't just a minor inconvenience. When we ignore them, they introduce label noise. This noise can significantly impair the performance of SPML. So, it's clear that we need to address these issues to improve the accuracy and effectiveness of our models. Begin iframe, frame title our related works, begin itemize, item overview of AN loss and focal loss, begin itemize, item AN loss performs poorly across all datasets due to the false negative noise introduced by AN assumption. Item focal loss is ineffective in dealing with the interclass imbalance in SPML. End itemize, end iframe, Let's delve into some related works. We have the AN loss, which unfortunately doesn't perform well across all datasets. The main issue here is the false negative noise that the AN assumption introduces. This significantly impacts the performance of SPML. Then we have focal loss. While it's a baseline method, it falls short in handling the interclass imbalance in SPML. This imbalance is a crucial factor to consider for effective SPML. So, there's a clear need for a more robust method, which is what our research aims to address. In this slide, we delve deeper into the concept of pseudo-labeling, a technique that has been instrumental in addressing the challenges of mislabeling in AN, pseudo, Labeling is a method that helps us navigate around the issues of false negatives, which are a common occurrence in AN. These false negatives are treated as noise within the system. Now you might wonder, why is this important? Well, effectively managing these noisy labels has been shown to significantly enhance the performance of SPML. This is a key aspect of our research and forms the foundation of our proposed framework. In the next slides, we will explore how we've integrated this concept into our work. In this slide, we delve into the challenges that single positive multi-label learning, or SPML, faces. The first hurdle is the extreme intraclass imbalance. This refers to the disproportionate distribution of positive and negative labels within a single category. It's a significant issue because it can skew the learning process and affect the model's performance. The second challenge is the interclass imbalance, which is also known as the long-tailed effect. This occurs when there are many more instances of some classes than others, causing the model to be biased towards the majority classes. These imbalances pose significant obstacles in SPML, and addressing them is crucial for improving the performance of our models. In the next slides, we will discuss how our proposed method, the generalized robust loss, tackles these challenges effectively. In the realm of single positive multi-label learning, or SPML, we've seen some interesting approaches to address the imbalance issue. One such approach uses both entropy maximization and asymmetric pseudo-labeling. This method has shown promise in tackling the intraclass imbalance in SPML. However, the issue of positive-negative label imbalance in SPML is still a relatively unexplored area. This imbalance is a significant challenge in SPML, and finding effective solutions to this problem is crucial for improving the performance of SPML models. As we move forward, it's essential to delve deeper into these mechanisms and explore innovative ways to address these imbalances. Begin a frame. Frame title: A theoretical and experimental validation of GR loss. Begin itemize. Item theoretical validation. Begin itemize. Item empirical risk estimates for SPML derived. Item gradient analysis performed to understand the behavior of the loss function. End itemize. Item experimental validation. Begin itemize. Item GR loss tested on 4 benchmarks, achieving state-of-the-art results in most cases. Item ablation study and hyperparameter analysis conducted to understand the impact of different components. End itemize. Item limitations and future work. Begin itemize. Item need for dynamic adjustment of robust loss parameters. Item evaluation on different backbones required for comprehensive validation. Item correlation among classes not considered, affecting performance on certain datasets. End itemize. End itemize. End frame. Begin frame. Frame title: Our solution. The generalized robust loss function. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data 2405.03501 v1 figures 2405.03501 v1 figure 2:2.png captiona tinea the generalized robust loss function. End a figure. Begin itemize. Item our approach. Begin itemize. Item we propose a novel loss function, the generalized robust loss GR loss, to tackle the challenges in SPML. Item this function uses a soft pseudo-labeling mechanism to compensate for missing labels and a robust loss design to handle noise and pseudo-labels. Item we introduce 2 tunable functions, K, beta, and versus alpha, to calibrate model output, addressing both intraclass and interclass imbalances. Item despite some limitations, our GR loss has shown promising results in both theoretical and experimental evaluations. End itemize. End itemize. End a frame. Begin a frame. Frame title: A theoretical and experimental validation. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A SRC task underscore execution extracted underscore paper underscore data 2405.03501 v1 figures 2405.03501 v1 figure 2:2.png captiona tinea empirical results and comparison. End a figure. Begin itemize. Item validation of GR loss method. Begin itemize. Item empirical risk estimates and gradient analysis performed. Item achieves state-of-the-art results on 4 benchmarks. Item identified limitations and future improvements. End itemize, end itemize, end frame, backquote. In this slide, we delve into the validation of our GR loss method. We've conducted a thorough theoretical analysis, including empirical risk estimates and gradient analysis, to ensure the robustness of our approach. Our method has been put to the test, achieving state-of-the-art results on 4 benchmarks. However, we acknowledge that our work has limitations. We've identified areas for future improvements, including dynamic adjustment of robust loss and consideration of class correlation. This will guide our next steps in refining the GR loss method. On this slide, we delve into the technical aspects of our research, focusing on the gradient analysis. As you can see in the figure, we've conducted a comprehensive analysis of the gradients involved in our proposed GR loss method. Now, let's talk about hyperparameters in GR loss. We have 4 hyperparameters determined in the method. For each dataset, 2 of these hyperparameters are fixed. The selection of these hyperparameters is crucial as it is based on the best mean average precision, or MAP, on the validation set. This approach ensures that our model is not only robust but also adaptable to different datasets. In the next slides, we will further discuss the implications of these hyperparameters and how they contribute to the overall performance of our model. Begin frame title a theoretical and experimental validation of GR loss. Begin a figure. Centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data, 2405.03501v1, figures, 2405.03501v1 figure 2:2.png, captiona, tiny empirical results and gradient analysis. End a figure. Begin itemize. Item validating GR loss. Begin itemize. Item we validated the effectiveness of GR loss both theoretically and experimentally. Item theoretical validation includes deriving empirical risk estimates and performing a gradient analysis. Item experimental validation shows our method achieving state-of-the-art results on 4 benchmarks. End itemize. Item limitations and future work. Begin itemize. Item despite its effectiveness, our method has limitations, such as static hyperparameters and lack of evaluation on different backbones. Item future work will focus on overcoming these limitations for further improvement. End itemize. End itemize, end frame. Backquote. In our research, we introduced a new loss function, the Generalized Robust Loss, or GR loss, specifically designed for single-point multi-label learning, or SPML. This function uses a soft, pseudo-labeling mechanism to compensate for the lack of labels, and a robust loss to handle the noise introduced by these pseudo-labels. We also incorporated 2 tunable functions to calibrate the model output, addressing both intra-class and inter-class imbalances. Our experimental results, obtained from 4 SPML benchmarks, VOC, COCO, NUS, and CUB, show that our GR loss outperforms most existing methods. However, it falls slightly short on the CUB dataset, where it ranks second to MIME. This is due to our method treating SPML as multiple binary classification tasks, which can lead to inferior performance when there are more categories, and thus more positive labels for each image. Despite these promising results, our study has some limitations. For instance, we set certain parameters in the robust loss as static, when a dynamic approach might be more effective. We also did not evaluate our GR loss on different backbones, and our method does not consider the correlation among classes. Addressing these limitations could further improve our work. In a separate experiment, we verified our assumptions by dividing the VOC and COCO validation sets into 100 intervals and calculating the ratio of false negatives to missing labels. The results were consistent with our assumptions, further validating our approach. Backquote. Begin frame title experimental verification and analysis. Begin a figure. Centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data, 2405.03501v1, figures, 2405.03501v1 figure 5:1.png, captiona, tiny false negatives to missing labels ratio analysis. End figure. Begin itemize. Item, experimental findings, begin itemize. Item, initial training stages show a constant function, aligning with assumption 1. Item, final stages of training reveal a monotonically increasing function, consistent with assumption 2. Item, these findings validate the assumptions made in our model. End itemize, end itemize, end frame. In this slide, we delve deeper into the technical aspects of our research. As you can see in the figure, we've conducted a gradient analysis to further understand our model's behavior. Now, let's discuss some insights from our results. Firstly, we found that treating single-point multi-label learning, or SPML, as multiple binary classification tasks has its benefits. This approach has allowed our generalized robust loss, or GR loss, to outperform existing methods in several benchmarks. However, it's not without its challenges. When dealing with datasets with a higher number of classes and stronger label correlation, our method showed some limitations. For instance, in the CUB dataset with 312 classes, our method was slightly outperformed by MIME, which considers label correlation and interclass differences. These insights highlight the potential of our approach, but also the areas where further research is needed. We believe that understanding these nuances is key to advancing the field of SPML. In this slide, we delve into the technical results of our study. As you can see from the figure, we have compared the mean average precision, or MAP, of our proposed GR loss with different hyperparameters on the VOC dataset. This comparison is crucial as it helps us understand the effectiveness of our method in handling single-label multi-class problems. Our GR loss method consistently outperforms other existing methods in the first three benchmarks, namely VOC, COCO, and NUS. However, it falls slightly short on the CUB benchmark, coming in second to MIME. This is primarily due to our method treating SPML as multiple binary classification tasks, which can lead to a stronger correlation between labels and thus slightly inferior performance. Despite this, the improvements we've seen on VOC, COCO, and NUS benchmarks are significant, and we believe our GR loss method holds promise for further research and development in this field. Begin our frame. Frame title future directions, begin itemize. Item, addressing limitations, begin itemize. Item, we aim to improve the dynamic nature of the robust loss, enhancing the balance between fitting ability and robustness. Item, we plan to evaluate the GR loss on different backbones to further validate its effectiveness. Item, we will consider the correlation among classes to improve performance, particularly on datasets with a high number of classes like CUB. End itemize. Item, expanding applications, begin itemize. Item, we believe the GR loss has potential applications beyond SPML, and we look forward to exploring these possibilities. End itemize, end itemize, end frame.